Okay, good morning, good afternoon, good night to everyone. So we'll start this tutorial right now. It's part of the ALife 2022. Thank you to organizers for giving us an opportunity. It is recorded and it will be uploaded to YouTube. So I hope it will be useful for people who listen now or later. I will be doing the presentation, and my co-organizer, Dr. Sheryl Chang, is also in the audience. Both of us are actually having COVID at the moment. I'm pretty much recovered, but I'm still having some residual cough. So if I go in a fit, I'll probably mute myself for a while. And in any case, we'll have a break after 45 minutes, maybe just for a short while to recover a little bit. So without any further ado, let me start. I will be talking about agent-based modeling of pandemics. And in doing so, I will introduce some work that we have been doing in the Center for Complex Systems at the University of Sydney over the last 6 or so years. Because it's a tutorial, I will obviously go into some nitty-gritty details of agent-based modeling and also use a few case studies. The first will be influenza modeling that we've done prior to 2019, and then COVID-19 modeling, which we are continuing at the moment. So the canonical example of a major pandemic, global scale pandemic, is Spanish flu, and quite a significant impact on the whole world, with fatalities reaching 3 to 5% of the world population. And you see, I mean, the number of infected is pretty much 500 million, and at the time the population on the planet was about 2 billion. So quite a major impact. And what I want to show next is a series of plots, so just one plot comparing a few major cities, New York, London, Paris, and Berlin, in terms of fatalities across 1918 and 1919. And you see what now is a well-recognized epidemic curve signature, with a very quick onset, exponential rise, a well-formed peak, and a decline, which is as rapid, with an interesting kinks. For example, in this wave here in London, you see that this wave goes down, slows a little bit, and then continues on a decline. And I'll talk about that kind of signature, what causes it as well, because it's quite reproducible, and it's not a fluke. It happens quite often. And obviously what happens also quite often is the emergence of secondary waves, which repeated the pandemic pretty much around the world, maybe not as synchronized as the first wave, but pretty much synchronized the next year. And that's what we're observing right now with COVID-19 pandemic, which is different in some ways, but in terms of this resurgence of the disease, it is quite similar. So why is it the case? How do you model this kind of multiple waves? What would be the underlying reasons? That's part of the questions that we'll be trying to unravel. So obviously, in going through different kinds of modeling, and the tutorial is about agent-based modeling, but I'll start with actually compartmental modeling, which is well known. In modeling this phenomena, you have to pay attention to methodological details, and in this tutorial I'll talk about methodology as well, quite a lot, but also you want to talk about some research questions that many modelers are trying to answer, as well as some pragmatic questions in terms of predictability or optimal pandemic response. So the tutorial is not structured in these blocks, but I will be interleaving bit by bit methodology, research questions, and maybe some practical recommendations and advice. So we had a look at this historical perspective, and 100 years later, in 2018, Bill Gates put this by now very famous quote. I mean, basically he said that he had hoped that the 100th anniversary of the Spanish flu pandemic would spark a lot of discussion about whether we're ready for the next global epidemic. And unfortunately it didn't, and we're still not ready, he said 4 years ago. And it was quite true, as it turned out, that the society was not really ready for a serious discussion and a serious response, which needed to be quite novel. We're facing right now a novel coronavirus, and in many ways we have not been prepared in early 2020, and in some ways we are still not prepared even now. So I put here this plot basically to show that the waves are quite pronounced. This is Australian context, and if you look at the normal scale, not the log scale, at a period of time from the very beginning, and the first wave in Australia started to shape up in March 2020, when it was followed by the second wave of the same ancestral type, Wuhan lineage, which lasted even for longer, but mostly was concentrated in Victoria, one of the states in Australia. Then the nation eliminated, I would say, or suppressed it very efficiently, eliminated this coronavirus for quite a while. You see that we enjoyed a long lull until in mid-June we had an imported case, and we even know who that person is. The Delta variant arrived, and an exponential rise followed, resulting in a wave which peaked at around November 2021. And why am I showing you that? The first two waves were essentially mitigated by non-pharmaceutical interventions. Social distancing, stay-at-home orders in general, other measures, non-pharmaceutical, while the third wave required a combination of a lockdown and a vaccination, because this lull was not really used to vaccinate the Australian population to any significant degree. In mid-June, we had less than 5% of adults vaccinated, and a rapid progressive rollout, which ramped up, reached 2/3 of the adult population and 20% of children in this age group by mid-October. And in combination with the lockdown, it essentially controlled the epidemic, which started to go down. Unfortunately, then the Omicron variant came and the story sort of repeated. So one methodological comment I make immediately here is that when you look at this behavior expressed in just incidence in terms of case numbers, you essentially may lose the context. Is 2,000 cases a day a lot? And you should actually be comparing it in terms of per million, cases per million. And logarithmic scale that you see here is a more fair comparison, simply because it allows to compare fractional changes systematically across multiple scales. For example, a jump of 10% from 9 to 10, or 90 to 100, or 900 to 1000 will be shown in this scale similarly. You see pretty much the same three waves here, and then the Omicron wave, which continues to unfold in Australia, and now it's winter in Australia, obviously. Whether it's seasonal or not, I wouldn't dare to say, but I doubt it. I think it is just the lack of boosting, vaccination, and a lack of non-pharmaceutical interventions like social distancing and mask wearing, which allows this new peak to form. And we're only modeling this at this stage, and I wouldn't guesstimate whether the next peak will exceed the previous one. Hopefully not. Okay, so that's just a historical background, and I go even further in history, back to the era of Spanish flu. It's a very famous paper by Kermack and McKendrick, which started the compartmental models in epidemiology. In this instance, it was susceptible, infectious, recovered. I will not spend a lot of time talking about it, but historical perspective is that these people try to explain that sharp exponential rise and sharp decline in mathematical, elegant formulation. And they came up with this very famous model, which concisely represents this epidemic development, pandemic development, in terms of just three variables: X, Y, Z, the number of susceptible people, the number of infected people, infectious, and the number of recovered people. Altogether, three compartments add up to the total population. I'm sure you're familiar with it, but just to remind you that the number of susceptible population reduces given the interactions between susceptible and infectious, XY, in proportion to this number with the transmission probability kappa. This compartment reduces, and the number of infectious people grows with the same kappa. However, some of the infectious people recover in proportion to only Y, because you don't need interactions to recover. And then it's reduced by Ly, where L is the recovery rate. And all of that population goes into the recovered component. So all that you need to know about this model, essentially, that two variables, kappa and L, and lambda, okay, and L, or beta and gamma in modern notation, drive this dynamics, and beautifully it does create that sort of epidemic curve. So if you look specifically at what happens over time, the susceptible population, which starts, say, from the total number of individuals in this particular town, say 500, it reduces until everybody becomes susceptible and healthy, and there is no reinfection, there is no loss of immunity. The recovered people, there are no recovered in the beginning, and then everybody is recovered at the end. So what happens to the infectious is is shown with the green curve. It goes up exponentially, peaks, and then starts to go down. And just before this peak, essentially the number of recovered individuals start to exceed the number of susceptible, which obviously is related to this dynamic. Again, introducing some well-known ideas, I will be talking about reproductive ratio R0. Technically speaking, R0 is reproductive number. It's the number of secondary infections that a single patient, say patient 0, for instance, generates in otherwise susceptible population. So at the very beginning, when nobody has immunity, nobody recovered, everybody is a potential victim of a disease. Say in case of Ebola, R0 is 2. So a patient 0 on average would infect 2, each of which would also infect 2. You see, this picture is seemingly very simple, but the more people get already infected and therefore immune, you will start getting some red faces here, reducing this spread. But in the very beginning, R0 is in otherwise susceptible population infects that many. In SARS, in the original SARS, R0 was 4, right? And again, methodologically speaking, when the epidemic progresses, you are no longer talking about R0, you're talking about R effective. And that number obviously takes into account that the blue compartment reduces and there are practically nobody at the end to infect. So the very same disease would be infecting fewer and fewer and fewer. So when R0 is higher than 1, you get an epidemic. And when R0 is less than 1, or when R effective drops below 1, you start getting a decline, or in case of R0 being less than 1, you don't even start up, going to go up. So why do I say reproductive ratio here? Because in the context of this model, compartmental model that we just looked at in a different notation, beta is a transmission rate and gamma is a recovery rate. The ratio beta divided by gamma is exactly identical to the reproductive number R0. And therefore, people who were trained in the tradition of compartmental models, and say 20, 30 years ago, that was all the population of epidemiologists, people started to conflate the reproductive ratio R0 with the reproductive number, because beta divided by gamma is exactly the reproductive number. But in different other models, it's obviously incorrect to talk about reproductive ratio because it's no longer the ratio of these two probabilities. It's similar, but not necessarily the case. And in agent-based models, you have to take a particular care. That's why I spend so much time talking about it. Okay, so why do we even do agent-based models? You could just do elegantly, concisely, and on average, very correctly. You could do epidemic modeling with compartmental models. But different sort of questions bring the need to more higher resolution modeling, because you may want to zoom in different areas nationwide, for example, in Australia, at the progression of an epidemic. And that's, for example, here, what you see is a snapshot of a particular day of influenza modeling, in this case, with the color indicating normalized prevalence in each of the local areas defined according to some geographic standard. In this instance, I think it is SA2, maybe it is SA1, I forgot. So zooming in and looking at this quite asynchronous, not very smooth distribution of the disease, you start asking the question, would I be able to model that with a compartmental model? And obviously the answer is no, you cannot model that with 3 numbers. 3 numbers assume you have essentially 3 colors, which are uniformly distributed across the nation. Well, you could model maybe compartmental models in each of these areas and have a set of these models. But the further you zoom in, the more difficult it becomes to distribute it geospatially. And the second type of question is, where and how do you intervene in order to bring it under control? And in a compartmental model, the only way you can even pose this question is to say what should be the R effective to bring it down, right? And what is the R effective, for example, at any particular time? So you could say that to bring the epidemic, which starts with R naught 4, you need to bring R naught 3/4 down, 75% down. But how do you do? What measures do you need to take is unclear in these models. While if you do it in a more high resolution way, you can answer these questions, and that motivates a lot the use of agent-based models. Okay, so what is agent-based model? Here I'm using a slide from Bank of England, which had an agent-based model of a financial market. You represent individuals, in this case, people or banks or households, as entities which are situated in some environment and are able to interact. This particular picture is actually slightly misleading because for any figure here, you see only a fixed number of agents with which it's connected. So it almost looks like a network-based model, and there are a lot of confusion why people might perceive agent-based model as a network-based model. But it's not the case despite similarities, because although representation may look like that, may look similar, you do not model in an agent-based model, you do not model say progression of a disease along a predefined specific edges. You don't know what they are. What you do instead is you could say, for example, in this context, in this whole ellipse, you could say, well, if you have those red agents as infectious agents, then anyone, say all the green ones, for example, are susceptible, any green one could get potentially probabilistically infected, while the purple ones may have been already recovered and therefore immune. So you need to define a probability rate at particular time slice for a green person to get infected as a result of a potential interaction with any of the red ones. So you could check, would this green susceptible person be infected from that one, or from this one, or from that one. So you need to check anybody in this context. And the complication is that you may have multiple contexts. You may have a context in a household, lots of interactions, lots of family members who might pass an infection, many opportunities, even in a given day. Another context could be household cluster, your neighbors, with whom you interact less frequently, so the probability of infection is smaller. You could have a neighborhood, you could have a community like a shopping mall, and obviously you have working zones or destination zones in terms of the census. I'm switching nomenclature here, basically places of work or places of study where you interact during daytime only. So building this context from data is difficult, so that's where demographics come in. And then defining this interaction contact probabilities of infection as rates per day or per half day is also quite difficult. But what you buy as a result is a very high resolution picture, so you could actually zoom in at any statistical area, whether it is a street or maybe a suburb or city or state, and see at any given time what's the snapshot of this disease. How did it all come about? So I'll spend a little bit more on history because it's a tutorial, and it's not a presentation of any particular research result that we produce. It's quite instructive to look at the inception of this whole idea in the context of pandemic simulation. One inception happened in Los Alamos National Laboratory, where people developed a large-scale, very large-scale molecular dynamic simulation of, say, 19 billion particles. That was a paper in 2004. And that's how it looked like. That's a snapshot produced by this scalable parallel short-range molecular dynamics spasm simulator. So essentially, particles in close proximity interact with neighbors, and these interactions may change their physical properties, like polarity or electrical charge or magnetic charge or whatnot. And there are laws of interaction defined in terms of these physical quantities at that local scale. But as a result, by simulating in a discrete time these interactions, you could get snapshots which represent a macro property, which may be important for whatever purpose you're simulating this, which may define at some mesoscale or macro scale what this material might look like, or what this particular medium might have as an attribute, as a property. Then the next step, and that's the paper published in 2006, the same group of people, pretty much, and you see their names, Tim German and Kai Kadao and others, had this idea that you could actually simulate pandemic development, unfolding or diffusion of the disease, say influenza, using the same, or obviously adjusted, adapted simulator, but the same idea, where the particles would become people who are in some sort of proximity, and the properties that you change are not electrical or magnetic charge or polarity, but rather susceptible, infectious, recovered states. All you needed to do, and that's obviously a big task, is to define the rules of interaction. When you deal with physical particles, you know what they are from physical laws. But when you deal with probabilities of transmission for a particular variant, say H5N1 avian influenza or H1N1, you need to define them fairly carefully. So where do you take them? That would be another question. But assuming you define them, and I'll get back to that question, but assuming you define them, you could then have a simulation at the macro scale, at the scale of a nation, United States, starting from a particular day 0 and infecting people, for example, in international airports, if it is a pandemic scenario, and seeing that, say, looking at the left, where you don't have any interventions or anything, the disease progresses starting from this seeding points. On day 65, you have obviously very visible points where it starts, but by day 85, the color indicates that it has diffused quite significantly. And like I said in the beginning, one of the motivating questions was not only to see a nice geospatial distribution, but also see how and where and in what way can you intervene. So on the right-hand side, you see a result corresponding to the same virus and the same timeline, day 65, day 85, but with a targeted antiviral prophylaxis. So if you cover 60% of your population before the pandemic with targeted antivirals, or even when the pandemic starts, you actually deploy this antiviral prophylaxis in a targeted way, which is defined again, specifically whether you target individuals in the proximity to the seeding points or in some other way preemptively, you could see that even at day 65, you pretty much controlled the epidemic, you contained it at the source. And that's what you could actually do with agent-based models. You could simulate effects of very refined, detailed interventions at a high resolution still. And the intervention in this particular instance that I'm showing you, and the paper deals with multiple types of interventions, is targeted antiviral prophylaxis. So you choose which agents you give these antivirals. A compartmental model would not be able to do an analysis like that with a targeted intervention. So let me then switch to something that we've been doing in influenza modeling, because we need to speed up a little bit and get into maybe more nitty-gritty details. Most of the agent-based models have these three layers. The demographics, because if you want to have a high-fidelity model, which represents millions and millions and millions of agents, where do you get the data on their residence, or where they work, and who do they interact with? Even in completely privacy-preserving anonymous ways, you still need data sources to generate these large populations. It's taken from usually from census data. And that's what we do as well. Then given travel patterns, commuting patterns, including long distance, you could actually catch quite a lot of potential interactions, not only in households where people live, but also across distance, like children going to schools and people going to work. And finally, this infection rates, these transmission rates, as well as the natural history of the disease in the infected individual, in each of them, you need to define it and calibrate it specifically to a given virus. And devil is in the detail, right? So when we did pandemic influenza modeling, we focused on H1N1 specifically in terms of this epidemiological layer. Obviously, demographics and mobility do not depend on biology of the virus, but the natural history of the disease does. So in terms of research questions, and I'm switching the context here, you could answer very interesting questions, not only in terms of predicting the peak, but you could say how synchronous or asynchronous is the development, diffusion of the disease across a nation. Do you have one wave or two waves, like this bimodality? Do you have maybe some important critical regimes or tipping points? You could look at the effects of urbanization comparing across different years. You could compare urban and regional waves. You could do a counterfactual analysis. You could say, well, what if the situation was different in some ways? What would have happened? And then you could actually check what's the efficiency of different interventions, either geographically targeted antiprophylaxis. For influenza, antivirals are obviously available, unfortunately not for COVID, or contact-targeted anti-prophylaxis tab, or vaccination, which we do for COVID. We use this, and then we moved on to COVID-19 modeling, and what we modeled is encapsulated in this open source software, agent-based model of transmission and control of COVID-19 pandemic in Australia. It uses 24 million agents calibrated to census data, representing multiple contexts like households, household clusters, neighborhoods, communities, and the working groups. And we did model at least the first three waves, and the last wave of Omicron is in progress, our modeling of. So the features of this software, and partially this tutorial is dedicated to this software. I will not obviously go into showing you C++ code, but when you download and look at it later on, you will be able to very quickly see what different variables, different parameters mean. At the very high level, we represent the composition of households across different local areas, household sizes. We represent commuting patterns. We talk about different infection seeding scenarios. Do we start only in Sydney, or do we start in all major airports? We allow transmission within mixing context. So a mixing context is essentially like a household cluster, neighborhood like a street, community, and a working group, or a classroom in school. It was critical to deal with different age-dependent ratios for children and adults when we modeled COVID. That we had to change. In influenza, it was pretty much homogeneous. It was also quite important to model vaccination rollouts with multiple vaccines, because that was the practice in Australia and in many other countries, like Pfizer and AstraZeneca, for instance. On top of it, it was important to model different components of vaccine efficacy. I'll talk about that in more detail, but the idea is that there are different efficacies in terms of preventing a person from getting infected. So you're shielding from the outside transmission, but also you may get infected, but you may not develop any symptoms. And some efficacies are known to be fairly high for preventing the disease. But even if you do get a disease, you may not be transmitting as badly. So the efficacy in terms of transmission is the third component. And in the first year, we didn't have vaccinations, vaccines. So we needed to vary social distancing in trying to see under what circumstances you could control the pandemic. So I did mention this household or different mixing contexts in terms of household composition, and you see it slightly better here. But I would say that each of the dots here, each agent, is modeled in terms of its demographic attributes, its commute pattern, like this agent might work in this area, and this agent from the same neighborhood might work in another working area, another destination zone. Once infected, a susceptible agent becomes exposed, infectious, and then recovered. So the natural history of pathogenesis of the disease is a particular profile developing over time, and that's another important parameterization that you need to develop if you want to use agent-based models. The compliance levels are defined for different non-pharmaceutical interventions, different NPIs, in terms of case isolation, in terms of home quarantine, school closures, and social distancing. And another set of attributes for each agent is the vaccination. Basically in terms of vaccine efficacy components, set of 3 numbers. And there are other attributes. So you see that there is quite a lot of parameters that you need to define and distribute across agents, because it doesn't mean that each agent has exactly the same parameters, right? I mean, some agents might be compliant with home quarantine, but not with social distancing overall in the community. So I will not talk about demographics a lot, but believe me, there was a lot of work trying to create artificial surrogate population given the census distribution, because the census usually keeps the data in anonymous ways. So to ensure that privacy is preserved, some noise is introduced to prevent any reverse engineering of who is who. And therefore, given this noise, you get some loss of aggregation, to recover from which we needed to come up with an algorithm so that the artificially generated population still has on average the same properties that match the aggregate characteristics of the census. Okay, so the first paper that we published, and it's a good source if you want to look into that, was in Simulation, Modeling, Practice, and Theory. And you see that, you see here, for example, that commute distance distributions were not easy to reproduce, but they do a good job in matching the census characteristics in terms of travel to work data. That's what we call mobility. Maybe it's not the best name to call travel to work data because we don't model infections on transport, but it helps connect different areas, including long distance. And so the disease could jump from one place to another, which is very important. Otherwise, you would see pretty much very synchronous development of a pandemic in sorry, in sort of concentric circles centered on the seeding locations. So in modeling pandemics, you usually start, when you do it at a nation wide scale, you start with international airports, and you see that in proportion to passenger traffic, which is well known, and that part was not easy, it was not difficult to model. This part, and I'm looking at the natural history of the disease, is very important. It's crucial. If you don't get it right, you will be modeling a very strange disease. And even if you get some aggregate predictions being right, that would be essentially a fluke. There is an important methodological consideration here, that when you model something in a very general sense, you could get some semblance of truth, but you also want to have your mechanistic representation being faithful to what epidemiologists know about the disease. Because look, at the end of the day, you could take a neural network, feed it with some input data, and it will produce an output, a good prediction, right? But that way would not give you any mechanistic fidelity. You would not be able to interpret what happens in terms of, say, symptomatic probability of infection versus asymptomatic probability. You would not be able to say what's the incubation period or what's the recovery period. It may not matter if you want to do only the prediction, but if you want to change the model and compare across different variants, you cannot compare two neural networks in terms of the weights of their nodes or edges. So here you get a fairly simple, essentially triangular profile where infectivity goes up until some peak is reached, and then it goes down. So the probability of infection is assumed to be 1 at the peak. It's normalized to that, and it's assumed that it's linearly decreasing over time. It's a simple model. For asymptomatic individuals, the probability of infection at the peak is assumed to be a fraction of 1. In this case, say 0.5, but it could be any number, 0.3, for example. The generation period is another important characteristic that is derived given this profile and given the simulation, starting with some particular R naught. And essentially it shows how many days are between, say, onset of symptoms in one patient and in the patient which is infected, in the agent which is giving the infection and the agent which is receiving the infection, on average, across multiple simulations. So in case of H1N1, the generation period was known, and say for R0 of 1.5, the generation period is between like 3. In our simulations, around 3.36, for example, which is within an acceptable range known by epidemiologists. So you verify or validate your model. You verify your model in this way. So you calibrate some parameters so that something that you know about this particular disease fall within this range. So it's a very important part of the model. Without getting it right, you don't have a chance really, unless by coincidence to get your simulations right. Another example, slightly more refined, of something like natural history of the disease shows, for example, that you may get across a range of agents, you could get different infectivity profiles, like, some agents may follow the red profile and some agents may follow the green profile with, slightly different probabilities of infection over time. So where do you get the probabilities of like interaction probabilities or contact probabilities, and what do you do with them? Because what I showed you is what happens to probability of infection that an infectious agent, gives to somebody else. But probability of one does not mean means it's highest probability, but it doesn't mean that anybody in the neighborhood gets it, right? So looking at this in function f, which is the probability profile like that, right, over time. That's why it has n minus nj, where j is the day. J is the agent and n is the day. So this function is giving you at any given day a number taken from this natural history of the disease profile. Given this number, you pick up from the table like this above a specific probability rate given the context G. So the context G could be household of a particular size, it could be school, it could be grade in a class, could be working area. So essentially these numbers are taking from some prior studies for respiratory diseases, and this table might not even change. That table basically is about frequency of contacts in a particular household or a particular school, basically in a particular context. So these numbers need to scale up or down given a particular disease. Obviously, it may so happen that even these numbers change in relation to each other given a new disease. But until many decades pass, you won't know this refined change, but you may know that kappa, which is a global scalar, scales them up and down with a different variant or different virus. So that's how you compute the probability of infection from infectious agent J to a susceptible agent I in the context G. Well, as I mentioned, there are multiple contexts, and you need to check not only for all agents J in a given context, because that is only for one pair, one potential interaction, But you obviously, first of all, you have multiple agents in this context, and then you have multiple contexts for each potential susceptible agent who may potentially get infected. So why do we have this 1 minus something and 1 minus something? It's a probability of not being infected. So you multiply probabilities of not being infected given some potential infectious neighbors. And once you multiply them across contexts, that is the probability of you being not infected. And 1 minus that recovers it back to infection probability. So this kappa is actually a proxy of that R naught. It's not identical to it, but it is very close, and with some calibration, you do get to see that they go hand in hand. Okay, so I think that is pretty much the nitty-gritty detail that you need to know if you want to do agent-based model. It is the extent of the complexity which is involved. Once you define these numbers and you define how to multiply some probabilities, essentially you run one huge loop across agents, all susceptible agents. And for each of those, you check who are their infectious neighbors in every of the contexts. So it's a loop within the loop. Okay. I'll probably skip that because this was an explanation of where do you get these numbers from originally. It's a study by Koshemes, very influential study. You could have a look at it. And they go at a great depth deriving these numbers. And then you also get numbers from similar studies, defining it for interactions in working groups and communities and so on and so forth. So what happens here is it's a scary formula, but it's not scary at all. It's back to this discussion of reproductive ratio R naught and reproductive number. What happens is that when you get an agent-based model, how do you get your reproductive number given kappa? Because kappa is something that we calibrate, if you remember. It's an input parameter, but how do you know what R naught it results in? You essentially run a very abridged simulation, maybe 10,000 times. In this abridged simulation, you infect one person at random and see how many people get eventually infected. And it's abridged because every infected person does not infect anybody else. So you only count immediate secondary infections. And that's what you sum up at the end. And you get in one simulation for one particular agent, you get 5 infections. Another random run, you could get 10 infections, or 0 or 1. And then you basically average across these numbers. That would have been simple. However, as we realized after a while, there is a subtle problem. I usually do not talk about that in our presentations, but in a tutorial, I have a chance to explain what actually happens. You see, definition of R naught is how many secondary infections a typical random agent, random case would generate in otherwise susceptible population. But when you randomly select in a population of, say, 24 million, you randomly select an agent, you still have a bias because you may select somebody like a child, 0 to 4, years old. You may select an adult which is retired, not working, not employed. And these age groups have actually different attack rates. And given a particular R0 or particular scalar kappa, you may sample this population by just uniformly randomly selecting a random person. You may introduce that bias because you sample something which is already biased towards high infectivity or low infectivity. Because if you just select out of these 5 age groups, like one of each, and you sit somewhere at kappa 3, you will give obviously more weight by this unconscious bias to people in this age group, which infect a lot more. Sorry. So to counteract, you simply re-weight. You apply another weight in proportion to this attack rates. When you add up these numbers, you add the age stratified attack rate dependent on agent I or agent J rather, who is your index case. That's all there is. But you need to do it because otherwise you get a different R0, not the one which actually happens there. And it's important to do it because, as I mentioned, R0 of 1 gives you a critical threshold. So if you do it just with a random sampling, the epidemics would start from R0 being something like 0.75 or 0.8, which is not what it's supposed to happen. But if you do it with the weight adjusted attack rate, weight, you get precisely what's theoretically predicted around R0 of 1, which is nice to know, right? So it means that you're doing the right thing with your simulations. While we're talking about R0s, I'll just show you a very simple comparison of different R0s. You could get a higher R0 and then it goes down quicker, or you could have a very low R0, like practically no epidemic, like say R0 1.25, and then the tail is going fairly long. And again, do notice that we have this kink, like a secondary wave shaping up, but not quite forming. And finally, another wisdom that you get from epidemiological textbooks is that the herd immunity threshold is defined as 1 minus inverse R0. So if R0 is say 2, 50% of the population give you the herd immunity, meaning that the people who are not immune yet get protection indirectly by the rest having already having been infected. An interesting research question that we looked at was this question of hierarchical spatial spread or wave-like diffusion. Like wave-like diffusion is more like these concentric circles growing around each of the points where you get infection. And this hypothesis was verified by good people long time before us, who pointed out that it's actually hierarchical spatial spread rather than wave-like diffusion, meaning that it usually happens in in big, agglomerations rather than simply going geographically like a wave-like diffusion. So it depends on the urbanization, it depends on density of the population more than on the distance. So the size of communities mean more than geographic proximity. To bring that question of asynchrony back, you look at the time going down, 2 different scenarios. Again, it's influenza. We're using the old simulator here. R0 1.5, R0 2.0. Over time, you start getting, you start from international airports and you start getting some asynchrony of average prevalence. And at the end of the day, you could see that the long tail here still keeps the infection going, while a shorter tail with higher R0 burns it quicker. So by looking at these different areas, you could actually compute how synchronous or asynchronous it is at any given time. Basically, you look at comparing this average prevalences or prevalences at any given time, average across areas, whether they have, what's the variance of that distribution. That's what asynchrony or synchrony is. And when you look at this variance or inverse variance, rather the synchrony, you see that it is more correlated with the size of the area. The larger the area, the more synchrony there is, rather than with the distance, which would have been just geographic. Because if it was dependent only on the distance, synchrony would simply be going down. The further it is, the less synchronous it is. But it goes actually up and only then down, while here it mostly goes up. So that's a type of a research question you could be answering in these models. Okay, and then I'll talk about this effect of urbanization versus effect of, say, increasing international traffic. That was all a paper published before COVID in 2018, and it was based on the influenza modeling. Let's not spend time on that. Here we'll only talk about increasing urbanization in Australia, with the fraction of the population living in cities increasing and the fractions living in remote regions decreasing. International traffic, again, driven by multiple passenger flows. And here in this study, we compared 3 different census years, 2006, 2011, 2016, and therefore we looked at passenger traffic at these 3 years. And that's the first 2 results here. If you see that exactly in the same way, and the epidemiological parameters are exactly the same, for example, you deal with H1N1 influenza, you see that simulation of 2006 shows that the red curve shows that the peak is lower than 2011, which in turn is lower than 2016, and it happened later. So with more urbanization, you bring the peak earlier, it happens earlier and higher. Same disease, just different urbanization, different densities. And here I'll bring this point about an interesting kink forming. You see, in a decline of any curve, say 2016, you get this inflection. And it actually happens because you have 2 underlying waves. One which is happening with the first peak, and the second wave happens at a smaller level, smaller scale, and therefore it's kind of hidden. But superposition of these 2 waves gives you the curve which you see usually at the aggregate level. So you could say, how do I know that there are 2 waves? Maybe it is just a mathematical nicety. But these 2 waves are, first of all, identifiable, and I'll show you how. And second of all, they have very clear geographic meaning. So look, for example, at a different representation of this epidemic, not in terms of infected individuals, but in terms of numbers of areas which peak on a particular day. Say I take day 50. How many areas peaked in their own small individual area-dependent curves? How many of them peaked on that day? And then you simply count like a histogram. It's not even a histogram, it's a time domain curve. How many areas peaked on that day? And you get two waves, say in 2006 and 2011 and 2016. But first of all, you could use the scala to distinguish pretty much very clearly the green curves, the first peak, the first wave with the urban centers. And the pink areas are all regional, all rural areas. So you see that because the pandemic starts in major airports, it spreads within these urban centers, and only then it reaches inland, and these areas tend to peak later. There is some overlap, obviously. So the first result was about the peaks happening earlier and higher, but the next result was to show that these two waves, if you go from 2006 to 2011, get slightly further apart, with urbanization wave happening in a more pronounced way. So that was also an effect of urbanization. And so to conclude, I will show you an example of counterfactual analysis distinguishing two effects, urbanization effect and increase in international traffic. How did we distinguish them? Well, it's a simulation with an agent-based model. So you could take a population of 2006, or you could take, for example, a travel of 2016, international travel, and put it in 2006. So you could basically seed it with the international passenger arrivals from 2016 and see what would be the delta with just 2006. And you see that the peak in the first wave, and it happens around day 50, pretty much goes to zero, which means that the seeding conditions have much larger impact on the first wave. So if you take the seed of 2016, you kill the difference. And that's logical. The international travel drives the first wave. But the second wave, which happens around day 70, does not seem to reduce this delta. In fact, the delta is fairly high, which means that the international travel, which is represented by the seed, does not do much for the rural wave. So that's another example of what you could do with the agent-based model. Okay, so here I suggest that we have a short break, maybe just, literally like maybe 4 or 5 minutes, and then come back at, or maybe in 4 or 5 minutes. I don't know what time you have exactly there. Okay. Well, yeah, so we'll continue now, and I'll just wrap up this tutorial using this case study, which is really on our mind, COVID-19. We did the adjustment to the model in terms of epidemiology early in 2020. As I mentioned, it was crucial to change the natural history of the disease. And you see that the infectivity now goes in a kind of more smooth way. The recovery period is much longer. The asymptomatic infectivity may be lower, but there is a lot of asymptomatic infection happening in general for longer and from early period. For children, it's different in comparison to adults, and so on and so forth. So it was quite successful after this recalibration, and starting with the R0 around 2.75, we managed to produce these predictions. The orange curve is a prediction which we produced around day 45, and the black dots are the actual observations. And you see that the time of the peak was predicted fairly well, and even the amplitude, we're looking at relatively small numbers, hundreds of cases for the first wave, was well captured. The prevalence was also well captured. So it gave us good validation for the model. Then we started looking at what do you do to control it, and social distancing or extent of stay-at-home restrictions. How many people, what fraction of people stays at home during this non-pharmaceutical intervention was our key parameter, in addition to other ones that you see here in the table. So social distancing is defined in a very holistic way here. It essentially defines a fraction of people who stay at home and reduce interactions, not within households, but within community and within workplace. So in workplace, they pretty much don't interact anymore, and within community, say 50%. In terms of the model, that's why I spent so much time talking about this first equation, the product of these probabilities. The adjustments go as follows. This fraction of people who stay at home define which agents, J, no longer infect others. And if they do, they infect them with essentially smaller probability. So if I no longer interact at workplace, that zero pretty much reduces any probability of infection to zero. That becomes one, becomes one, and the resulting probability is zero. If it's 50%, then the force of infection halves. So it's a very elegant way in an agent-based model to represent social distancing. As a result, and that's a very important result in this whole development, is that there was a tipping point, a phase transition in social distancing. If the extent of the population reducing the interactions is only 70% or less, the epidemic continues to go up. It obviously slows down, but still continues to go up. While if the population which follows, which is compliant with this social distancing restrictions, is 80% or above, you get these curves which go down. The gray area is the period of duration of the social distancing. Once it stops, the curves go up, but it buys you time to maybe develop a better response, develop vaccines, buy these vaccines, and so on and so forth. So the predictions that you saw earlier was produced by this orange curve, which follows 90% reduction in interactions. Another view at the same phase transition is this profile across all layers, and you clearly see a ridge formed somewhere between 70 and 80%. The new model, which we developed in 2021, which is slightly more complicated because we introduced detection probabilities, because not every case is detected. We changed again incubation period, distributed with the different mean, and so on and so forth. Those details that I only show them here, so you know that every time you get a new variant, you need to recalibrate your model and validate it again, and only then make predictions for a sufficiently long horizon. Another example of complexities that we deal with is that these profiles that I showed you, triangular profiles, are actually different in every given agent. they are only distributed around the same mean. But this is, again, a power of an agent-based modeling. So for the Delta variant, we calibrated it again. Because previous one was alpha, and before that was ancestral strain. And the mean R0 was around 6.2, which is much higher. I'll skip this parameterization. It shows you, however, the extent of parameters that you may need to think about. It's not a mind-boggling number of parameters, a dozen at most, right? And then the parameters in terms of social distancing had to be adjusted as well, because to deal with the Delta, you needed even to curb the community interactions to something which is practically infeasible. That's why I don't think if any country succeeded in suppressing, controlling completely the Delta variant. Only with vaccination it became possible. But again, it was buying you time to complete and finish the vaccination campaign. I did talk about this vaccination efficacies, and it's important to point it out again how these components combine in the efficacy that that somebody tells you it's 0.9 efficacy, because efficacies against the disease and efficacy against infection to begin with combine in this interesting non-linear way. You sum them up and you subtract their product. So if you have 70% efficacy against symptoms and 70% efficacy against even getting infection, they combine in this way to 0.9. And that's what you get in reports from, say, Pfizer or Moderna or something like that. While if they are 0.5, they don't have to be the same. They could be different. Something in this range, 0.305, for example, they could combine the 0.75 or 0.65 clinical efficacy. Why is it important? Because going back to the herd immunity threshold, it needs to be divided by the vaccine efficacy. It's not only 1 minus inverse R0. You need to divide it by the vaccine efficacy. And if vaccine efficacy is 0.9 and R0 is like in the first wave, yeah, you could get 0.7 herd immunity threshold. Everybody was waiting for it to happen. You vaccinate 70% of people and you're done. However, with vaccine efficacy lower, for example, 0.8, and R0 of 5.5, the number becomes meaningless. It exceeds 1. Basically, you need to vaccinate more than you have in the population to get herd immunity. It's meaningless. That's why herd immunity for R0 of 5.5 or higher with this still fairly high efficacies is not a possibility. So these efficacies, again, staying at methodological level, need to be added to this formula, which builds up slightly further. But again, it's still a fairly nice and simple, elegant formula, which is again implemented in the same loop within the loop computationally. So we already multiplied the rate by the force of infection of socially distancing people. And now you multiply them by the efficacy against transmission on the infection side. On the receiving side, you multiply it by efficiency against susceptibility. And finally, once you get this PIN, you multiply it by fraction of symptomaticity in adults and children, and you use efficiency against the disease. It's a very simple formula. So to conclude, I'll give you this prediction that we've done for the Delta variant using this recalibrated model at 25th of August last year in terms of 3 scenarios: 40% social distancing, 50% and 60%, and then we let it go and just observe. And the scenarios what we already said are the limits of the extent of people's compliance. 40 to 50 at that time, they stayed within these limits, and the prediction stayed within these limits as well. So that was a validation of this model. A very important, and that's the second important research result or even practical result, is that a small increase in social distancing could reduce hospitalizations threefold. So a small change in social distancing from 40 to 50, and then from 50 to 60 reduces it threefold here, and then further threefold there. Same effect applies for ICU, occupancy, intensive care units, and for fatalities, it's twofold reduction for every 10% increase in social distancing. And again, the model was used for that clinical burden at 24th of September last year, and it stayed between 40 and 50, much closer to 50 for the duration of this modeling exercise. So again, validating with the 3 months ahead prediction, in this case 2 months, was something quite remarkable. So to finalize, I would say that we have very important challenges in this modeling that agent-based model actually allows you to solve to good extent. But there are still challenges. We talked about tipping points. We talked about amplification effects. We talked about vaccination efficacy, but it diminishes over time, and uptake and SD levels are uneven across demographics. And to succeed, they must be met for all population subgroups. So equity of vaccination targets is an important societal goal. Declining compliance with SD, fatigue is important. Multiple waves start to interact here. So all of these are challenges. But the agent-based models, or modeling in general, is a good recipe because it has a lot of strengths, and I mentioned them, I won't repeat them, but it has weaknesses. You need to calibrate few parameters, and you need to use high-performance computing. So these are two weaknesses which are solvable, but you need to be aware of them. So I'll skip over the wish list. Lots of things you could add to the model, and I will only have the slide here showing that there is open source of this Amtrak 19. This is the link here on Zenoda, and we keep updating it, and another update is coming in maybe a week even. And the paper which describes it to a very detailed level is this one, popped up in February in Frontiers in Public Health. Supplementary material is very extensive. You're welcome to download this code, and we are very open to collaborations. If you want to adapt this model to another nation, to another region, please get in touch with us and we'll be happy to help. There is obviously README file there and a user guide, 10 pages or so. So it's possible to run it even without talking to us, but we're happy to help. And finally, this is the team. Sheryl here is in the audience, and Cameron standing next to me, and on the right-hand side, it's Nathan and Oliver. So thank you. That's a shameless plug of a special issue that we are preparing at the moment. If you're interested, just have a look at it. And finally, the references. So thank you.